Good morning. My name is Chandramouli, lecturer in mechanical engineering, worked at Government Polytechnic Warangal. So, subject engineering materials. So, in that major topic is iron carbon equilibrium diagram. So, today we discuss I cooling and solidification of metals and alloys. In iron carbon equilibrium diagram, cooling and solidification of metals and alloys and allotropic form of iron. It is a very important special property for allotropic form or polymorphism of iron. So with the help of PPTs, animations, photos and diagrams. So we will see the what is the special property of iron. Already you will see the allotropic, which process means iron carbon is alloying, that means interstitial solid solution. Which type of alloying used means interstitial solid solution alloying. So interstitial solid solution alloying, where is the means available of vacancy positions. So we will do the interstitial solid solution alloying. In that, iron behaves different types of properties, exhibits properties means different types of structures exhibits at different types of temperatures. How will form all these structures detailed, we will see this in today's class. So recap, in this previous class we have discussed about what is the phase rule, Gibbs phase rule and equilibrium diagrams. At the same time, solid solution, that means types of alloyings, that means solid solutions, chemical compound and mechanical mixtures. And also you will see the cooling curves of pure metal, alloy and solid solutions. In that you will see our syllabus iron carbon equilibrium diagram is a solid solution. In that it is a category of interstitial solid solution. So in that you see the Gibbs phase rule, that means P plus F is equal to C plus 2. P plus F is equal to C plus 2. Easily remembering, police firing 2 constables. That means P plus F is equal to C plus 2. That is a very important relation for the evaluating all phase or equilibrium diagrams. So quick review of last period. Phase is a form of material having characteristic structure and properties. Phase is a form of a material having characteristic and structure and properties. A phase diagram shows relationship between composition, temperature and structure. It is a very important. A phase diagram shows the relationship between the composition, that is alloying, and temperature and structure. All these are evaluating phase diagrams or equilibrium diagrams or S curves or C curves. All these are the phase diagrams. Equilibrium or phase diagrams are used to complete a description of an alloy constituent. So in our syllabus, iron carbon equilibrium diagram is iron carbon equilibrium diagram. In iron carbon equilibrium diagram, how the alloying means interstitial solid solution alloying. So in which composition, which type of temperature, which type of structure is getting. You will correlate all these three important factors. That is, the equilibrium diagram shows relationship between the composition, temperature and structure. This is the very important for we will review this class. So today's objective on completion of this period, you would be able to know cooling and solidification of a molten metal, cooling curves for alloy and solid solution, and mainly we discuss polymorphism and allotropic form. So first you will see the cooling of a liquid metal. Already we will discuss all these things, but this is a basic for every material, liquid material. That's why once again we will discuss cooling of a liquid metal. Crystallization occurs around a small nuclei which may be impure particles. The first crystals have the crystal shape into which the metal would be naturally solidified. For example, face-centered cubic in case of copper. So as a crystal grows, it tends to develop spikes and its shape changes into a tree-like structure is called dendrites. Already you will see in the third chapter crystallization. So first we will form the nuclei, then it grows to nuclei. First the formation of nuclei, then crystallize. So next after that formation of nuclei, crystal growth is starting. So along with this crystal, these two factors are going on. So in primary axis, secondary axis, and tertiary axis. So these any direction, that means like a tree-like structure, that is called dendrites. Or dendritic structure. Already we discussed in crystallization of a metal. So as dendrites grows, the space between its arms fill up. Outward growth stops when growing arms meets other. So eventually the entire liquid solidifies and there is a little trace of the original dendritic structure, only the grain into which the dendrites have grown. So you see the solidification of metal. This is the overall diagram. So first, liquid, a small nuclei act as a centers for crystal growth. Second, a small dendrites begins to develop their nuclei. Third stage, dendrites continues to grow. The fourth one, as the dendrites grows in the space between them fill in. So fifth stage, the solidification is completes. A little evidence of dendrite structure remains, that is grinds and grind boundaries. So this is the total solidification of metal. So like that we will alloying two materials. You will see in this diploma syllabus binary system alloy to mix the two materials. So that's why you will study the solidification of a metal. So next you will see the thermal equilibrium of a diagram. In thermal equilibrium of a diagram, when a pure water is cooled to 0 degrees centigrade, it changes the states from liquid to solid and ice is formed. The cooling curve shows a plot of temperature against time. So that means down to 0 degrees centigrade, the water only exists in the liquid state. At 0 degrees centigrade, solidification starts to occur. So while it is happening, the temperature remains constant as the latent heat of fusion is lost. So you will see the cooling curve of a water during solidification. So temperature versus time. So that means TTT diagrams means time, temperature and transformation. That is a very important for to study the equilibrium diagrams. So T, time, temperature and transformation. Which type of structure or state is there, that is the liquid state, solid state or gaseous state. You will see the TTT diagram, temperature versus time. So it above the so liquid state to 0 degrees, so it is exist as the liquid plus solid. So this means there is a cooling curve, that is the cooling curve. So above 0 degrees centigrade, this is the liquid state. At 0 degrees centigrade, So these quite cooling. So means decrease the temperature, that is the process cooling. So liquid state. So at 0 degrees centigrade, liquid plus solid. So remaining after some time decrease the temperature, it is a ice. So different types of cooling curves, that means occurs. So that means that is a pure metal. A cooling curve of an alloy, you are mixing two or more elements. You see the cooling curve for a particular composition. So different types of compositions occur. This type of cooling curves occurs. That means a cooling curve for alloy, all pure substances shows similar behavior with alloys. There is no single temperature palette. So, and the range over which solidification occurs depends on the proportions of the elements in the alloy. The point A and point B referred as arrest points, and the temperatures at which occurs at the arrest temperature. That means the phases or changes. That is called arrest points. So you see the cooling curve of a solid solution, that is liquid phase, means temperature versus time or transformation. So where liquid phase starts and liquid phase and solid phase, liquid phase and solid phase, liquid phase and solid phase, liquid phase and solid phases. Liquid phase and solid phase are both are intermediate phase or occurs. Then finally solid phase is occurs. That is means phase change starts up temperature, phase change finishing starts off. So that is all are seen that TTT diagrams: time, temperature and transformation. That is a liquid phase transformation. So next all are, you will see the lower critical temperature, upper critical temperature. So all how the alloying or transformation TTT diagrams occurs. TTT diagrams: time, temperature, transformations. You will see the phase diagrams where we see all these are caused by the experimental setups. So after that solidification of metals, you will see the thermal equilibrium diagram. Already it is shown. While this is happening, temperature remains constant at the latent heat of fusion last. So that is the cooling cause of water during solidification. This is for alloy. So after that, you will see the cooling curves of a solid solution, different types of solid solutions, TTT diagrams: time, temperature, and transformation. All these are used for the all are useful for to evaluate the phase diagrams or equilibrium diagrams. So TTT diagrams for alloys, you will see here lower critical temperature, upper critical temperature. So means suppose you draw the TTT diagrams: time, temperature, transformation. So in these diagrams, so take decomposition of iron with the combination of the iron carbon equilibrium. So in that different phases are occurring, that is called upper critical temperatures and lower critical temperature. That means transformation starting points, transformation ending points. All are these are arresting points. These are very very important to evaluate phase diagrams and equilibrium diagrams. So before that you will see the what is the polymorphism or allotropic form. Polymorphism or allotropic form. So, polymorphism or allotropic form is a physical phenomena. Is a physical phenomenon where a material may have more one crystal structure. A physical phenomenon where a material have a more than one physical structure is called polymorphism or allotropic form. A material that shows polymorphism exists in more than one type of space lattice is called in the solid state. So if the change in structure is reversible, that the polymorphism polymorphic change is known as a allotropy. So it is a very different property for iron. So cooling curve, you study the cooling curve of a pure iron or allotropic form of pure iron or polymorphism of a pure iron. Suppose you will see the iron cooling curve. So you will see the temperature in terms of temperature versus time and transformation TTT. So in the temperature is in the Fahrenheit and so in this polymorphism you will see. So above 1538 degrees centigrade it is in the form of iron liquid. In the terms of Fahrenheit 2800 degrees centigrade. So before you cooling, this is a reversible process, cooling or heating. So we will cool the iron. So in between 2800 Fahrenheit to 2554 Fahrenheit, it is called, the type of iron is called delta iron. The type of iron is called delta iron. The type of iron is called delta iron. So next in 2554 degrees centigrade to 1666 up to this type of iron is called gamma iron, and 1666 to 1414 Fahrenheit, all are in terms of Fahrenheit, is called alpha iron. So you see temperature versus time transformation in the cooling of the pure iron. At different temperatures it exhibits different type of irons and it exhibits different types of structures also. So delta iron gets BCC structure. BCC means body centered cubic structure. Gamma iron is called FCC structure, that is a face centered cubic structure. These all are the non-magnetic properties. So below 1414 Fahrenheit degrees centigrade, it is all our magnetic properties. So and 1666 to 1414 1414, that is alpha iron, it exhibits BCC structure. It is a non-magnetic. Below the 1414 Fahrenheit, same alpha iron with magnetic properties, that is called beta iron. So suppose you will observe this cooling curve for iron, pure form of iron. So different temperatures it exhibits same one form of iron, it exhibits different temperature, different types of structures, that is delta iron, gamma iron and alpha iron and beta iron. So delta iron exhibits BCC structure, gamma iron exhibits FCC structure, alpha iron exhibits BCC structure, and beta iron exhibits BCC structure with magnetic and non-magnetic properties. So we will observe different temperatures, different structures it exhibits. So this type of property is known as a polymorphism or that is next polymorphism or allotropic form. So in this different types of irons. So delta iron is a unstable form of iron, means high temperatures it is not a stable, it is a unstable form of a delta iron. So most stable form of iron is gamma iron at the temperature of 2554 Fahrenheit to 1666. So this type of iron is called more stable form of iron. It is called gamma iron. It exhibits FCC structure. So it is very important below the 1666 degrees centigrade. So this is a alpha iron with all are above 14 Fahrenheit, all are above magnetic property, non-magnetic properties. So below the 14 Fahrenheit, 14 Fahrenheit below they are magnetic property. So this is called beta iron. So the structures are very important. So at different temperatures, it different allows cooling, so it exhibits different properties. So this property is known as a allotropic form of iron. That's why it is useful. Different temperatures, different types of irons are getting, and we will combine with carbon. So different types of invariant reactions are occurs. So you study the all invariant reactions in the phase diagrams or equilibrium diagrams. So you see the alpha iron is it is a structure of BCC, body centered cubic structure. In body centered cubic structure, so central atom 1 is there, so all corners 1/8 part of atom is there. You take unit cell of a BCC, total number of atoms per unit cell is equal to 1 plus 1 is equal to, you take a gamma iron. So gamma iron, it is a face centered cubic structure FCC. So all 6 faces is there. So 6 faces of atom is exist, remaining of is in the space lattice. Each corner 1/8 part. So total corner atoms is equal to 1 atom, and faces atom is equal to 6/2, that is 3 atoms. So total number of effective atoms per unit cell in face centered cubic structure is 1 plus 3 is equal to 4 atoms. So you will see this is the iron carbon equilibrium diagram. So in iron carbon equilibrium diagram, you will see the micro variation in microstructures in steels. So means iron carbon content, you mixing it. So different types of irons are, that means phase diagram, temperature and composition and transformation. All these are studies in the microstructures. So once you see the animation also. So you see the animation for allotropic forms, how this is. So first you see.
Iron represents perhaps the best known example for allotropy in a metal. At atmospheric pressure, there are 3 allotropic forms of iron: alpha iron A, Ka, ferrite, gamma iron A, Ka, austenite, and delta iron. At very high pressure, a 4th form exists called epsilon iron hexaferrum. Some controversial experimental evidence exists for another high-pressure form that is stable at very high pressures and temperatures. The phases of iron at atmospheric pressure are important because of the differences in solubility of carbon forming different types of steel. The high-pressure phases of iron are important as models for the solid parts of planetary cores. The inner core of the Earth is generally assumed to consist essentially of a crystalline iron-nickel alloy with epsilon structure. The outer core surrounding the solid inner core is believed to be composed of liquid iron mixed with nickel and trace amounts of lighter elements. Standard pressure allotropes. Delta iron. As molten iron cools down, it solidifies at 1595 degrees Celsius into its delta allotrope. which has a body-centered cubic crystal structure. Delta iron can dissolve as much as 0.09% of carbon by mass at 1493 degrees Celsius. Gamma iron austenite as the iron cools further to 1394 degrees Celsius. Its crystal structure changes to a face-centered cubic.
Hi, good morning. Today we'll be learning about the allotropic forms of iron with the help of the graph shown on the screen. So on this graph we have plotted the different temperatures and in the y-axis and the x-axis the time is shown, and the different forms of iron are also mentioned. So let's see. Iron has got these following three allotropic forms of crystal at different temperatures as mentioned over here. So the three forms are like alpha iron, gamma iron, and the delta iron. So the alpha iron are of two types. It occurs from normal temperature of 910 degrees Celsius and has got body-centered cubic lactic crystals. So let's see the two different forms of alpha iron. One is the ferromagnetic alpha iron, which occurs from normal temperature to about 770 degrees Celsius, and the next one is the paramagnetic alpha iron, which occurs from 770 degrees Celsius to about 910 degrees Celsius. So these are the two forms of alpha iron, and the next stage is the gamma iron, and this occurs from the 910 degree mark to about 1400 degree Celsius, and that is the gamma iron occurring process or gamma iron point at this particular temperature, and it has got crystal structure of phase-centered cubic lactics, and from there, that is 1400 degree Celsius to 1539 degrees Celsius, that is in molten state, we have the delta iron, and the crystal structure is body-centered cubic lactic, and this is in molten state. So these are the three variants of iron occurring in different temperatures: the alpha iron, gamma iron, and the delta iron. So I believe you got an idea about the allotropic forms of iron, and for more technical engineering videos you can visit my blog, that is www.techrexinfo.com, or my YouTube channel for more technical tutorial videos. Thanks for watching.
I had just started as an engineer working on the International Space Station, and I remember thinking, how...
So you'll see this type of
Hi, good morning. Today we'll be learning about
so you'll see the total this diagram. So allotropic form of iron. So in allotropic form of iron you'll see different temperatures. So in cooling, different type of structure. Same one material that exhibits different types of structures. That's why it is called allotropic form or polymorphism. So 1539 degrees in previous slides you will see the in terms of Fahrenheit. Here you will see the clearly in terms of degrees. So 1539 degrees centigrade is the melting point of iron. So below 1539 degrees to 1400 degrees centigrade, so it is called delta iron. So it is a high unstable form of iron. So it exhibits the BCC structure. So delta means BCC structure. So in 1400 degrees centigrade to 900, so 910 degrees centigrade, up to this type of iron, it is very stable form of iron. So this type of iron is called gamma iron. So it exhibits the FCC structure, face centered cubic structure. So next you will see the below the 910 degrees centigrade, so it is called alpha iron. So 910 to 770 or 763 degrees centigrade, so we have with non-magnetic property. So above the 770 degrees centigrade, all are these are non-magnetic properties. So below the 770 degrees centigrade is a magnetic property. So that is called alpha iron. With the magnetic property is called beta iron, that is called below the 77 degrees centigrade. And 910 to 910 degrees centigrade to 770 degrees centigrade, it is a so alpha iron with non-magnetic property. So you see, understand different temperature. So this is called cooling curve. Suppose you will see the heating, so that is also reversible process, so heating or cooling. So that's why in mechanical properties, temperatures in temperatures and composition and structure, these are the very important properties to alter the mechanical properties. These are very important factors, not properties, these are important factors to alter the mechanical properties. That's why first you study the same material with exhibits more number of structures with different temperatures is called allotropic or polymorphism of a material. So this is the very very important property of iron. Suppose you see the another animation.
हेलो फ्रेंड्स, आज हम बात करेंगे एलोट्रोपी ऑफ आयरन के बारे में। जब कोई मटेरियल
Iron represents perhaps the best known example for allotropy in a metal. At atmospheric pressure, there are three allotropic forms of iron: alpha iron aka ferrite, gamma iron aka austenite, and delta iron. At very high pressure, a fourth form exists, called epsilon iron hexaferrum. Some controversial experimental evidence exists for another high-pressure form that is stable at very high pressures and temperatures. The phases of iron at atmospheric pressure are important because of the differences in solubility of carbon, forming different types of steel. The high-pressure phases of iron are important as 98 degrees Celsius into its ice form. It is called gamma iron or austenite. I-cubed iron can dissolve considerably more carbon. This I-cubed form of carbon saturation is exhibited in stainless steel. Equals beta iron equals. Beta ferrite and beta iron are obsolete terms for the paramagnetic form of ferrite. The primary phase of low carbon or mild steel and most cast irons at room temperature is ferromagnetic ferrite. As iron or ferritic steel is heated above the critical temperature A2 or Curie temperature of 771 degrees Celsius, the random thermal agitation of the atoms exceeds the oriented magnetic moment of the unpaired electron spins in the 3D shell. The A2 forms the low temperature boundary of the beta iron field in the phase diagram in figure 1. Beta ferrite is crystallographically identical to alpha ferrite, except for magnetic domains and the
So after you see the animation for all these type of iron, so in this, so different type of structures occurs. So after the animation, you will see the allotropic different types of iron. So in that, so very stable form, you see the variation of microstructure in steel. So by alloying carbon content by the help of intentional solid solution alloying. That's why different types of structures occurs. So that means, so carbon percentage up to 2%, carbon percentage up to 2%, that is called steel. Carbon percentage up to greater than 2%, and up to the 6.67, that is called cast iron. So that's why, that is the reason why our carbon percentage up to 2% or greater than 2% means, so you will mixing the iron carbon alloy, that is a binary system alloy. In binary system alloy, so you suppose you do cooling or heating. So in 1539 degrees centigrade molten state of iron or liquid state of iron content, so you added carbon content maximum 6.67 percentage. So up to the 2 percentage is called steel. 0 to 2% is called steel. Greater than 2% up to the 6.67 percentage is called cast iron. So maximum solubility of carbon in iron is 6.67%. After that, it is saturated state. So that means it is a intentional solid solution. So vacancies are available up to 6.67%. 6.67% is okay. So suppose we will see how the microstructures of this alpha iron, microstructures of alpha iron and gamma iron are varying. Delta iron, alpha iron, gamma iron, delta iron are varying. So this is, you will see the microstructure of austenite and ferrite, and this is the equilibrium diagram. In equilibrium diagram, temperature is on y-axis, percentage of composition is on x-axis, and adding the carbon content and cooling this iron. So by adding the by adding the carbon content to the iron at different temperatures, different types of phases or occurs. Different types of already you'll see iron exhibits at a different temperature different types of structures, that is delta iron, gamma iron and alpha iron. In that, you will adding the carbon content. So where the stable forms are getting, where the stable form, or that is a useful form for the engineering applications are getting, that are all are evaluated in the equilibrium diagrams or phase diagrams or C curves or S curves. That is the main, very very important for the to evaluate all these structures and transformations at which temperature and which composition, which is the suitable material, which is the stable material, which is the useful material, which type of properties are occurs. So all these are, we will study the equilibrium diagrams or phase diagrams. That is very very important for the all this. Okay. So in this after that allotropic form, you will see the all these microstructures. So up to the steel, you will see this diagram, you will see the variation in microstructures in steel. So first you study the equilibrium diagram or phase diagram. So these components are easily understand: austenite plus cementoid, austenite plus ferrite, austenite. So all these components. So next ferrite plus perlite and cementite plus perlite. So how these components are occurs? So these all are seen in the our phase diagram or equilibrium diagram. So first we'll see austenite. We will see the different type of structure. 1.2% of carbonate dissolved in of a solid solution of FCC structure of austenite. So next you will see the cementoid. So as so changes that occurs in 1.2% of carbon alloy. So it is cooled from 1000 degrees centigrade. You will see the second component, that is a cementoid. So as cooling continues, the cementoid soaks up to the carbon until at 723 degrees centigrade. There is only tetratoid composition of the carbon left, which changes the perlite. So next you will see the perlite. It gives the steel containing cementoid Fe3C by the layered structure of the perlite. So what is the austenite? What is the cementoid? What is the perlite? What is the all of these are we will understand only we will see the iron carbon equilibrium diagram. So maximum amount of carbon occurs, that is 6.67. maximum amount of carbon absorbed 6.67. so that type of material is called cementoid Fe3C. It is the very hardest material. So 6.63 up to this is called cementoid. So most less amount of carbon content is ferrite, that is in the form of alpha iron. So delta gamma iron is the most stable form. Is called austenite form. So you will see the all are these are in iron carbon equilibrium diagram. So in that study of iron carbon equilibrium diagram, you will easily understand the structures, microstructures, how the compositions are varied, why these microstructures are varied. All are these are in detailed in iron carbon equilibrium diagram. So today's class only will study the different types of irons are that are polymorphism of iron or allotropic form of iron. So today's class summarized in this class we have to discuss about dendritic growth occurs during solidification. Solidification occurs differently for pure metal and alloys existing of different crystal structures at different temperatures is called polymorphism. If polymorphism is reversible is called allotropy. So all are today's summarized. So in polymorphism of iron at different temperatures different structures are getting. First one, delta iron, which exhibits BCC structure with high temperatures. It is a not stable form of iron. And next, very stable form of iron is gamma iron. Gamma iron easily to remember. Gamma means after that FCC structure, face centered cubic structure. It is a stable form of iron. It is a stable form of iron. So in most of engineering applications also this type of in the stable form of gamma and austenite. And next below this next alpha iron with magnetic and non-magnetic properties. Alpha iron with magnetic and non-magnetic properties all are seen in the allotropic form. That means temperature versus time and transformation. Temperature versus time and transformation of the diagram. So suppose you will see the quiz, different types of questions is there. First you will see the essay questions. Explain the neat sketch how the solidification occurs in the alloy. Explain the details of polymorphism and allotropy. Short questions: what is meant by dendritic growth? What are the different allotropic forms of iron? Define polymorphism, define allotropy. So what quiz? So what is meant by polymorphism? All of these are seen. So suppose you see total structure of iron. Okay, thank you.